Let's consider this autonomous linear dynamic system with n state variables. In expanded form, we have the derivative of the state variables are equal to a linear combination of the state variables themselves. We say that these equations are coupled, and finding a solution is not as straightforward. To obtain an easy solution, we propose a change of the basis of this description. And for the new basis, we use the right eigenvectors of the matrix A. We call this a similarity transformation, where the relationship between the original state variables and the new state variables, the vector y, is through this relationship. Q is the matrix of the right eigenvectors. And because they are linearly independent, then the matrix Q is invertible. Because of that, we can obtain also this relationship. How we obtain the transformation? We take the original set of equations and we multiply from the left by Q inverse. And as you can see on this side, the system now is transformed into a new set of equations where you have y that is equal to the matrix Q inverse AQ multiplied by y. As I discussed in a previous video, Q inverse AQ is equal to capital lambda, which is a diagonal matrix, and we have in the diagonal terms the eigenvalues of the matrix A. For the initial condition, because we have the definition of y and x here, you simply replace the value of x0, the initial value for the state variables, and that's how we obtain the initial values for the new state variables y. Because you have this matrix that is diagonal now, the set of equations we obtain here are decoupled. For example, the first variable, you have y1 dot is equal to lambda 1 times y1. And you can verify for the second variable all the way to the last variable, we will have that relationship. For a generic variable k, then we have this differential equation to solve. The derivative of yk is equal to the eigenvalue lambda k times yk with the corresponding initial condition. The only mathematical function that can satisfy this equation is an exponential function. So the solution for this has this form. Now that we have the solution for all the new state variables y, we can use the similarity transformation to obtain the solution for the original state variables x. So we have the matrix Q multiplied by the new state variables will give us the original state variables. But as you can see here, this is a realization of x in the new bases that are the eigenvectors of the matrix A. So all these terms that I have underlined here correspond to the solution of the new state variables y. They are just scalars quantity, but they are nothing else than the coefficient of the linear combination of the eigenvectors of A. So this coefficient will change in time, will change the linear combination to define what is the original set of state variables for the system. For a generic variable xk, all we have to do, we need to pick the k component of each of the eigenvectors, and we should have an explicit solution, as you can see here. In this solution, we need to differentiate three components. The first one is related to these exponential terms. These are called modes because they describe a type of dynamic behavior we might have in the system. Two specific cases could be when the eigenvalues are real. In that case, the exponential of this real quantity will describe either an exponential growth or exponential decay. But if the eigenvalues are complex, we will also have an oscillatory behavior with exponential growth or exponential decay of the amplitude of this oscillation. So those are two types of behaviors. And when you have oscillation, Also, that will be described with a specific frequency of the oscillation. The second component is related to the initial condition. Depending on the initial condition we have, this component, for example, for the first mode, this can be very large in magnitude. So if this is large, we say that the mode has been significantly excited and it potentially will show up in the state variables of the system. If you try a different initial condition, this term might be small in absolute value. In that case, the mode has not been significantly excited. That's why this part is related to the excitation of the mode. And the final component has to do with the k components of the eigenvectors. So this part is also known as the mode shape, and it will be related with how the mode is going to be manifested in the state variables. For the particular case that you have an eigenvalue that is complex and you will have oscillation, the angle of this component will be related with the shifting that the oscillation will have in the corresponding state variable.